Hello, everybody. We will start very soon in a few minutes. We wait for more people to join us, so we officially will start in a couple minutes. Thank you. Welcome, everybody. My name is Marcelo Vasquez. I am a CNL's Radiobiology Low Dose Research Head Section, and I will be today's moderator of this webinar. On behalf of the Canadian Nuclear Laboratories and our supporting partners, Atomic Energy of Canada Limited, Health Canada, and the Canadian Nuclear Safety Commission, thank you for joining. We are very excited to have Dr. Lawrence Dauer present today as part of our low-dose radiation webinar series. Also, we would like to honor Dr. Dauer by naming this special event the Bow Tie Webinar. So the goal of our webinar series is to help reinforce the connection between the research community by engaging world-leading scientists studying the biological effects of low-dose radiation exposure of different qualities and from different sources. If you have joined us before, you will note that we aim to have some time following Dr. Dauer's presentation to answer any questions. Please feel free to use the Q&A function you will see on your screen to write in these questions for Dr. Dauer. I will present your questions to Dr. Dauer at the end. And to introduce Dr. Dauer, I will hand it over to CNL Research Emeritus Dr. Edward Assand. Edward, welcome.
Thank you, Marcelo, and greetings to everyone, and welcome to CNL's Low-Dose Radiation Research webinar series. It is a distinct honor and privilege to introduce Larry Dauer, a pillar and a tireless worker serving the radiation protection community. Throughout his career, Larry made tremendous contributions to improving radiation safety practice in the workplace and enhancing radiation protection responsibility in clinical settings. Above all, Larry is a colleague and friend who is always there to assist. Larry is diplomat of the American Board of Health Physics. He is attending physicist at Memorial Sloan Kettering Cancer Center, radiation safety manager and chair of the Emergency Management Committee in the departments of Medical Physics and Radiology at Memorial Sloan Kettering. He has and continues to provide tireless service to radiation protection and health physics endeavors, whether in energy, industrial, or medical settings. His professional activities span many realms, from dose reconstruction to external and internal dosimetry, normal tissue toxicities, radiological emergency response, education and training, ethics, low dose rate effects, as well as risk communication, among others. Larry is fellow of the Health Physics Society and is recipient of its Elder Anderson Award. He has been chair, co-chair, and member of the program committees of numerous national and international meetings on radiation protection. His tireless service to committees concerned with risk estimates and radiation protection include the National Academy of Sciences, UNSCEAR, the ICRP, the US NRC, and NCRP is widely recognized. He has had leadership roles as chair and co-chair of numerous NCRP committees related to radiation protection of workers, patients, and members of the public. Larry is member and former board member of the NCRP. He is author of over 150 scientific papers and reports concerned with various aspects of radiation protection, as well as educational philosophies as applied to radiation safety, a focus of his doctoral training. In particular, Larry is scientific director of the million-person study led by Professor John Boyce. Today, Larry will share with us the latest on the US million-person study of low-dose rate radiation health effects, the importance, information, and innovation. Thank you, Larry, for taking the time to share your thoughts with us. Thank you.
Thank you so much, Marcelo and Edward. Mostly for the bow tie, trying to make bow ties cool again. Excellent, really well done. So I'm going to share my screen now. Thank you for the kind words and the opportunity to present. Is that working well? Okay.
Yes, perfect.
Okay, terrific. So today we will briefly go through the latest status on the million-person study of low-level and low-dose rate health effects. And along the way, I'll provide links to many of the papers that are associated where you can get, of course, detailed information and specific information. Once again, I thank the Canadian Nuclear Labs, AECL, and Canada, of course, generally for the opportunity. Feel free to reach out after the talk for continued dialogue. Disclosures are easy. Edward already went through. I am a National Council on Radiation Protection Measurements council member, a former board member, and currently as the scientific coordinator director assisting John Boyce, who is still currently the PI for the US million-person study. And the NCRP currently holds several grants and contracts providing current funding for the million-person study from the DOE, NASA, and CDC. So what I'd like to cover are why do a million-person study, who makes them up, how would you even go about studying a million persons, emphasizing that dosimetry is the key to high-quality epidemiology. In fact, without dosimetry, you could not do radiation epidemiology. Give you a sense of the comprehensive vital status and causes of death information that we've been developing for the million-person study, provide specific selected results so far to give you a sense of where things are heading, at least for about a little more than 500,000 of the million-person study. Talk about innovations that we're currently engaged in. For example, to link with Medicare in the US, that's from the Centers for Medicare Systems, so CMS. How quickly the million-person study has turned into a big data and big computing opportunity. And talk a little bit, very briefly, about NCRP ongoing and planned work associated with million-person study, and then cast a vision overall for what do we do next as this pulls together. Briefly, this is a U.S. national effort, both past and present. I think It's about 25 to 28 years in the making so far at this point, and each of these agencies have been a part of the million-person study over the years. Generally, why would we do this study? We have information at the highest dose rate and high total dose, generally, meaning somewhat above 100 millisieverts, perhaps 100 milligray to an organ. We don't really have good, solid information below that. And it's the very, does the dose make the poison? And because, it's difficult, for example, to talk about policy when, in the US, when we've set standards and limits generally against the atomic bomb survivor data, which is useful, essential, important to study, of course, but begs many questions: transfer of population, war-torn time, acute exposures, et cetera, et cetera. So why does it matter? Well, the need for health effects information is really large at low chronic doses. Most of the area where we apply policy, both in the United States and I'm sure up in Canada, are in chronic and low dose exposure conditions much, much more often than, say, an accident or some kind of acute or high dose situation. Occupational workers in medicine, if there were an accident or terrorism, really it would be about how much dose was left behind after cleanup, and then of course all the environment. So we really need information on the chronic and low dose piece. So the overall aim for the million-person study is to be the largest occupational radiation epidemiology study, and then to provide explicit scientific understanding of the health effects or potential health effects following prolonged exposure to radiation. And I list out here many of the reasons why it would make sense to have this information. Science should drive policy. We need good science to help drive policy. And who better to evaluate than the healthy U.S. worker population, since that's mainly a stakeholder, one of the important stakeholders in radiation protection policies overall. In addition to that, as we've developed over the years, the million-person study, we're recognizing that the construct of a million-person study is allowing or enabling us to answer important questions that we have not even yet asked. For example, radiation and cognition, or a detailed evaluation of cardiovascular outcomes. What about multiple stressors? And I'll try to talk a little bit about each of these as we go through the talk. Why 1 million persons? Why not 500,000? Why not 100,000 or 10 million? It has to do with an optimization piece. 1 million healthy American workers and veterans were chosen to get enough statistical power to evaluate impacts in the dose levels that we expected over a lifetime, say in the 25 to 50 milligray zone. And these are power studies that were done back in the 90s. And based on that, we think that we'll have enough power for evaluating cancer mortality, non-cancer mortality, certainly for rare cancers if you have 1 million individuals. We can assess intakes, doses. We can assess each of the doses, components, and include them. And we can evaluate differences, for example, between women and men, and evaluate whether or not there are indeed any differences that, or do we not see them at a chronic exposure condition. And then other conditions like cardiovascular disease, cognition or dementia, et cetera, et cetera. So if we can gather together this many, why not 10 million? Because studying 1 million is expensive, really expensive. And it would just be prohibitive to do a much larger study. Who makes up the US million-person studies to date? I've listed the general categories. There's several sub-cohorts, if you will, or categories of exposed populations. that include Manhattan Project and other Department of Energy sites. They make up almost a third of the study. Atomic veterans. If anybody's seen the movie Oppenheimer, almost everybody in that movie is in the Atomic Veterans Study portion of the million-person study. Nuclear power plant workers. You might call them the early workers up through until about 1985. Industrial radiographers make up a very large portion of the million-person study, and then as do medical radiation workers. We're evaluating nuclear submariners and other U.S. Navy individuals. We'll talk a little bit today about the radium dial workers. I think there was a total of about 4,000 or so, and we're able to study 3,200 of them. And that'll be a complete study, and I'll describe why that'll be important later. And then we have other smaller cohorts that will make up, probably just a little bit more than 1 million individuals. An important aspect, as important as having 1 million individuals chronically exposed, I think, are that it'll be by far the largest women radiation epidemiologic study ever conducted. So far, we have over 150,000 women. We'll have more as we complete the million-person study. And just for comparison, the number of adult Japanese female atomic bomb survivors is on the order of about 30,000, just to compare. Other comparisons against the atomic bomb survivor study. Overall, the number of folks who will be over 100 milligray or 100 millisievert or so in the million-person study will be on the order of about 80,000. And for the atomic bomb survivor study, that number is on the order of about 18,000. And then we have excellent dose distribution across the board. This slide also points out that in reality, we have about 7.5 million persons in the million-person study, although we have had to select in that lowest dose region to get us nearer to something affordable to be done, more like 1 million persons. So how do you go about studying 1 million persons? One thing, if you think about it, we work, say, for 30, 40, 50 years, depending on how healthy you are or how much you're enjoying your job. So we can kind of summarize it that the study is a minimum of a 50 million person year study. That is a huge study because we are collecting information on the person level. What job you were working, when did you work the job, what dose did you receive this year, what type of dose, what are your cause of death outcomes. In the future, we'll have your incident, disease and related outcomes. I'll talk about that later. So, you could de novo come up with 1 million persons, or to make it much more manageable, start and rely on previously studied cohort files. We had 40 years of published studies of small cohorts that were done, for example, as part of the Department of Energy evaluations. The atomic veteran population had been followed up by then the medical follow-up agency and then the Department of VA. And so we took that cohort and continued the follow-up, doing exquisite dosimetry on that group. And then we rely on available registries to supplement or form new populations. We're very lucky in the United States to have the Nuclear Regulatory Commission Radiation Exposure and Reporting System, REERS, and that system allowed us to put together, for example, the nuclear power cohort and the industrial radiographer cohort. For the DOE, a similar system is REMS, which includes all of the historical recorded doses and components of dose for those populations. And then we're working with the U.S. Navy, who has, since the beginning, the dawn of the nuclear Navy, kept exquisite dosimetry information at the Naval Dosimetry Center. And then commercial folks as well. Dauer is part of how we were able to pull together the medical worker cohort. Just to note again, dosimetry is key. That it's kind of interesting that there are certain quote unquote epidemiology studies out there that don't even include dosimetry. It's more about time worked or something. It's much. I mean, the only way we could do this is to have a excellent and complete dosimetry, and then of course complete vital status is key. Following up on the 50 million person years themselves, and then the million persons on cause of death, and identifying that and getting identifiers to be able to link all of that data together. All of these we've described in either NCRP reports that provide transparent how-tos or considerations for doing this, and we're following these, or in individual papers that I encourage you to look. Any radiation epidemiology study will, of course, have to deal with socioeconomic status adjustments or some way, direct way to evaluate potential for smoking or strong predictors of smoking habits. Education levels have been seen as a strong predictor of smoking habits, and we either have direct questionnaire information for individuals, or we've applied education level, occupational category, and in many cohorts, we've also included small-scale census block group residential histories to assign potential for tobacco use. The other item, I've emphasized it before, but for all million individuals, we have dosimetry monitoring and bioassay records for each of them, which are essential, and understanding how those have shifted over the decades and applying the very latest in radio kinetics and modeling to develop, for example, on the internal side, to go from bioassay to back to intake, and then forward to individual doses for each organ for every year following that intake. Just to remember, for those of us who live in regulated environments, that dose estimation in EPI is different than the regulatory reporting. Often in the regulatory reporting, you can put something like lower than a limit, or by law we have to use weighting factors when we do reporting in order to report millisievert, for example. In the case of epidemiology, we are aiming for absorbed doses to every organ or tissue of interest for each year following the exposure all the way until death. For external, it's the year of exposure. For internal, that's the gift that might keep on giving for at least the next 49 years, etc. And then we have another difference in dose estimation for epidemiology is that we have each component of dose. So low dose, a photon external exposure, internal exposures, high LET, low LET internal exposures, neutron exposures, tritium exposures, and each of these become a component of the dose that we can then evaluate after. And we do not apply weighting factors initially, because the whole idea of doing an epidemiologic study is to assess whether or not weighting factors might indeed be important or not. And so we can assess them in the analytic space after we build our database for the million persons. So often we're trying to get at annual dose to an organ, and so the NCRP and the ICRP have several very important publications that give us the roadmaps on how to do this, and we've been applying those transparently. In addition, the NCRP has developed several reports and commentaries. The NCRP report number 178 is an encyclopedic approach that talks about each of the category subcohorts of exposed individuals and how to go about deriving organ doses and the associated uncertainties focused on the million-person study. For certain cohorts, we need additional information. For example, the medical radiation workers, One very important consideration is whether or not an individual was wearing lead aprons, which from a radiation protection standpoint do a phenomenal job of reducing dose in certain medical exposure situations, but would be inappropriate if we didn't take that into account as we assess medical radiation workers' individual organ doses, for example. And then along the way, we are developing kinetic and anatomical models for different organs. Recently, we updated with the help, of course, at the helm was Rich Leckett and the ORNL Center for Radiation Protection Knowledge have developed brain dosimetry for internally deposited radionuclides. This is a major update, especially important for polonium, plutonium, uranium, and we discussed radium as well. So in other words, another way of looking at this is the very fact of chewing on how you would do this work has created science already in and of itself. Just to briefly talk about some of these worker cohorts, the Manhattan Project and other workers, we've already completed or just about completed the ones marked in blue. Mound Labs, Mallinckrodt, Los Alamos, Rocketdyne, Middlesex, and Rocky Flats is currently expected to be submitted for publication this year, Rocky Flats. We're in the process of evaluating the dose for about 39 to 40,000 folks at the Hanford Reservation. We have an initial evaluation of Fernald, and then the next ones on the list for us to do from the DOE Manhattan Project workers would include Oak Ridge as a site, which include K25, X10, and Y12, Savannah River, and then gaseous diffusion plants as well. The atomic veterans, I just listed a table here that included several series of tests that were done and how many individuals participated in those. Most of these were Navy veterans. And an assessment and evaluation of that has already been published, and you can go look at that as well. Medical radiation workers, what's unique about this cohort is half of them were male, half of them were female, so it's an important study from a comparing male and female outcomes. There's about 109,000 overall. Special guidance for how to deal with the lead apron, and their study of that cohort has already been published, and so you can look for that one. Industrial radiographers, there's about 125,000 industrial radiographers. We have already submitted, and we're now responding to the comments of the excellent comments by the reviewers. We expect to resubmit that to radiation research early this year, actually very soon, in the next month or so. A little more on the nuclear power plant workers. That study covers workers from 1957. These are U.S. nuclear power plant workers, 1957 through 1985. And we've gone through everything that I talked through, defining the cohort, evaluating and doing the tracing, etc. Why prior to 1985? Well, most of the exposure associated with the post-TMI mods occurred then, and then since then, ALARA and other excellent reductions in dose have occurred. And there are large numbers. It's really good dosimetry. You didn't get into the radiologically controlled area without having a badge, for example. There could be significant dose. In fact, there was significant dose, especially in the earlier years. You were able to get up to 30 millisievert at that time, considering 5 times N-18 guidance. Certainly some cumulative doses and organ doses on the order of a gray or more. The initial follow-up for this cohort was done through 2011. We're seeking funding now to update, give us another 10 years plus of follow-up, which would give us much more statistical power, though it's already a rather powerful study in and of itself. The dose distribution was broad for the nuclear power workers, as would be expected overall. And the exposure sources and scenarios are, there's a plethora of high-dose jobs. Most of the dose was received during outages. This is well understood. We understand that engineering controls and personal protective equipment was used very frequently, which really reduces on the potential for internal exposures, although there were a few individuals, of course, that had internal exposures. Most of the dose was during outage or maintenance activities. There is neutron exposures from a population standpoint. Those are low, but they are there for individuals. And then I just list off a whole number of higher dose outage tests that need to be understood. Those exposure scenarios could change. I'm just using nuclear power as an example of the types of things that we consider for each of the cohorts as we go through. And then in doing the nuclear power study, this is another case where science was added to the radiation protection community. We recognize that cranial caudal exposure were not insignificant potential exposures. So, for example, you might be a refueling operator and you're on top of the pool, so the dose is mainly from below. Or if you're a steam generator jumper, for example, your dose may be mainly from the tube sheet, which is above you. And so the good work by the Oak Ridge National Labs to develop cranial and caudal geometries to include with what you would typically evaluate for geometries for dose coefficients like AP or PA or left lateral, right lateral, rotational, or if you're in a cloud. So now we can add caudal cranial to our toolbox. And here we're just showing how we're getting to dose to the lung from various measures, either air kerma or HP10. And then what we do, just to walk you through a few examples, we begin by defining the population, and then we assess based on the follow-up at the time, a standardized mortality ratio, SMRs. I'm sure you've seen these charts before, where you're comparing the number of deaths in this cohort to the number of deaths in the US population, and this tells you lots of things. Overall, for all cause of death, standard mortality ratio for the nuclear power plant workers, for example, as in almost every cohort we have, shows that the causes of death are less in the worker population than population as a whole, and that's what is often commonly called the healthy worker effect. In other words, if you're a worker, you're healthy enough to be able to be working, and that's been studied by Monson and others for decades. And we see that in our populations. It would be weird to not see that in the populations, for example. But then you can see a few other heart disease is less than the normal population, all of the US population. But then other things jump out at you like pleura and mesothelioma, which is only caused by asbestos, and it's not shocking that we would see an increased risk of asbestos in nuclear power plant workers, especially early workers who dealt with pipes that were often insulated with asbestos during the 1957 through the 80s. Now, this isn't the whole picture, so the next step after doing this is to do what's called internal analyses within the cohort, where you have the 0 dose folks and you have the higher dose folks and everybody in between, and we evaluate those often with excess relative risk, ERR, and in the case of the million-person study, we often report that as excess relative risk per 100 milligray. And so I'll be giving some of those out later. But I wanted to emphasize that one of the keys for the US million-person study is to have open sharing of the data and results. As each cohort is finished, the initial studies are finished. We've been publishing papers in radiation research, health physics, and other IJRB and other publications. We had one whole special issue with over 25 papers in an IJRB back in April of 2022. You can go get a copy of that. But in addition, NCRP reports on the methods and the science and how we're evaluating are available publicly. We do virtual presentations and workshops. And vitally, all of the analytic data will eventually, and is as we develop over time, being posted to the Department of Energy's Comprehensive Epidemiology Data Resource, or CEDR, making this available for other folks to evaluate. So here are a few selected results so far. I'll go over non-CLL leukemia results. These are really important because in the atomic bomb survivor data, it appears that that may be one of the higher risks. You know, could be a factor of 10 to the third or 10 to the fourth, higher than others, depending on which group you're looking at. So if we were evaluating 1 million persons, even at rather low doses and low dose rates, chronically exposed over their working career, we would expect, if there was a signal, to see something in that area. I'll talk about all solid cancers, but with kind of a big asterisk that I'll discuss when we get there. Lung cancer, ischemic heart disease, because we know that that's of interest to the international community as a whole, and of course in the US, and certainly in Canada. And then we'll talk about Parkinson's disease as an example of one of the cognitive decline studies that we're evaluating. So I'm to move forward, just to clue you in as to how the discussion will go for the next few minutes. I'm going to try to provide the actual data from the nuclear power worker study and the very latest of the industrial radiographers that's still currently under review. Just to give you an example of how these look for each of the sub-cohorts as we're going through them. So here we're listing the dose response for non-CLL leukemia, and the excess relative risk per 100 milligray is listed in both, and you can see the values there. In both cases, the estimates are positive. In both cases, well, in the nuclear power worker case, it's technically non-statistically significant, although that dances right on the edge of statistical significance, as you can see with the dotted line laying along 0, basically. And what does this tell us? And another interesting aspect are that the slopes are within the confidence intervals of what the atomic bomb survivor data, perhaps a little bit lower, although we really won't be able to tell that until we pool all 1 million workers. Really, all we're looking at here in each of these cases is about 130,000 workers in each cohort. Not surprisingly, we see a signal. We would expect that. As a matter of fact, if you're doing an epidemiologic study of this size on radiation with this dose distribution, if we did not see anything here, we would frankly wonder whether or not we have issues with the methodology itself of doing the epidemiological study. So we'll continue to evaluate non-CLL leukemia. I give the specific values for each of the cohorts here, other than nuclear power and industrial radiographers, and you can kind of skim along that final column. Both the 95% confidence interval and the values themselves. You can, there are some, in addition, I'm listing the absorbed dose, mean and max for that cohort. So that's a useful tool. These are absorbed doses to the red bone marrow. Remember I said each organ for every year, and these are accumulated throughout the lifetime of the individual. So you can see the nuclear power plant worker mean doses were about 40 milligray, but the maximum danced near a gray, just for as an example. And then for the atomic veterans, those who are part of the 113,000, mostly Navy folks, although there were many others, Army and other veterans. Their doses overall are very low, although, again, the maximum dose, there's a large, broad distribution of doses, and they push a full gray for that group as well. So I'm listing here, showing examples of the dose response for all solid cancers so far in nuclear power workers and industrial radiographers, with a big asterisk. And here's the asterisk. You have to think about what we're looking at. We're looking at all solid cancers. So we know that there are several cancers that are likely not radiogenic that are included in an all solid cancer measure. So why would we do this? Mostly because the atomic bomb survivor study data has published this, so we would like this information to compare, and also because other worker studies, important worker studies, also report all solid cancers, and so we would like to do this. But we recognize that it's important for us to understand what the measure may mean, and I'll give you another good example here in a moment. So for nuclear power workers, just to summarize, it's basically a flat response. We don't see any significant ERR per 100 milligray. In industrial radiographers initially, and this is why it's so important to understand each of the cohort, each of the workers, and what's going on in that industry. Initially, it appeared that there might be very well a excess relative risk that was positive and statistically significant. However, remember I mentioned that workers who early worked with asbestos and insulation and piping, the SMRs for them had very, very high mesothelioma and asbestosis related deaths. And that is very, very true, most true, in fact, in the industrial radiographer cohort. And so what we really see here is a correlation between the amount of exposure one received is related to the amount of pipes that you peeled the asbestos back on, for example. So when we take lung and mesothelioma out of the all solid cancers list for the industrial radiographers, you can see the impact. The impact is we're back being flat. So it's really important as we pick through this data to understand the exposure conditions, and more than that, the actual work conditions for the workers. So when we evaluate all of these, we did a preliminary pooling. So what you're looking at is an initial estimate where we pooled together about 250,000 workers in a pooled analysis, and you can see the result is a very flat dose response for lung cancer. The dose response for lung cancer for each of the cohorts that have been completed are listed in this table. You can kind of skim through and see. Many of them are positive, but not all of them are statistically significant. Probably the most important line to look at here would be a further preliminary pooled analysis that we did where we actually pooled, not a meta-analysis, but we pooled together for one study, nuclear power plant workers, industrial radiographers, and medical workers. That's more than 300,000. It's almost 370,000 workers that represents. And the ERR at 100 milligray is very flat, 0.02, and not statistically significant. Now, we still need to incorporate a pooled study of the whole as we develop through, but this gives us a hint of where things stand at least so far. Now, lung cancer is one that we can evaluate male and female results, and I show the data here. But overall, there's little consistent evidence for a significant difference between females and males. This is really important because these are chronically exposed cohorts. Now, the atomic bomb survivor data appears to show a 2, maybe 3 times higher risk for females for lung cancer. We don't necessarily see that in our chronically exposed populations. In fact, we don't see much lung cancer risk overall, and we certainly don't see a factor of 2 or 3 at least so far in the small cohorts that we've been able to complete. Cardiovascular disease projections in the US continue to rise, and so this is a very important disease that we should be evaluating as an outcome. And so we're doing that, not the least, on the international level, and on careful evaluations have begun by ICRP and UNSCEAR and others to evaluate worker data and other exposed population data. So it'd be important for us to evaluate and report on the million worker cohort so far. And as you can see, for the nuclear power workers and industrial radiographers, there's basically a flat response. For ischemic heart disease, which is, one of the most important that we should evaluate. I do want to point out a very important fact, though, that each of these are for over 5,000 deaths. So this is a really big study in each of these cases. Out of the 135,000 in each of these cohorts, we have over 5,000 ischemic heart disease deaths upon which we can assess, and we have a rather broad distribution. So this is, as we pull together all of the study, the statistical power should really be helpful if we're trying to pull information that can support policy and science at some point. Here's a case where we have done a meta-analysis. We have not done the pooled analysis of all cohorts that are finished yet. That's going to take some effort, and we plan to do that, of course, and I'll talk about that in a few moments. But just to give an example, using meta-analysis, meta-analytic statistical attempts for for over 35,000 ischemic heart disease deaths, which is a really significant amount. We have, with the meta estimate, it's a rather flat response, and certainly not something jumping out as very positive at this point. So this represents all of these cohorts are probably about 530,000 workers with 35,000 ischemic heart disease deaths. So far, we haven't found evidence or consistent evidence for an increase in ischemic heart disease in the million-person study, and we just put that out there. Preliminary pooled data show similar results. We will eventually combine and pool all of the cohort data for all million individuals so that we can get a more powerful evaluation. What are the next steps from circulatory disease outcomes? Well, we're going to expand the dose response analyses to include all cardiovascular disease and cerebrovascular disease outcomes. And in fact, the latest cohorts have included an exhaustive list of those outcomes. And then we'll finish each of the cohorts and then eventually pool together. Perhaps as exciting as finishing the mortality portion will be the possibility to link with incidence data from the Medicare database, and which would be very helpful and perhaps give us much more information. So initially, NASA they came to us, the million-person study. The initial interest had to do with cognition. And Ray Bradbury once said, "It's not going to do us any good to land on Mars if we're stupid." Well, I mean, that's a bit tongue-in-cheek, but seriously, galactic and cosmic radiation has been shown in animal studies to lead to cognitive impairment, as I know many of you, a lot of work in Canada has been done in this regard as well. So it would be important to assess, if possible, cognitive outcomes, but could you do that in a human population? And NCRP report 183 discussed this in good detail, brought together experts in the field, and there was a recommendation to initiate studies initially of workers exposed to polonium, radium, plutonium, uranium, and americium, those high LET, even though they're not a direct galactic cosmic radiation corollary, they're near enough, perhaps even at the microdosimetric level, to make it worthwhile to assess the nearest terrestrial group that you could assess for that, and assess them for late CNS effects, cognitive function, dementia, etc. So NASA has begun, with the help of the million-person study, evaluating cognition and dementia in the million-person study cohorts to give another line of evidence. This is a photo of the latest 2020, the class 23 NASA astronaut educational corps. Eventually, these folks, every one of them want to fly at some point. Just to point out that Chris Williams is the first medical physicist astronaut on the list. So congratulations to him, and we look forward to his work in space. One of the evaluations that we're performing as part of those cognition studies includes Parkinson's disease as well as Alzheimer's. Parkinson's is the neurodegenerative disease, at least in the US, that's second to Alzheimer's. The overall prevalence is on the order of 7.1 million by next year, and certainly double by 2050. 1% representing about 1% of those greater than 60 years old. So if you have an aging population overall, there you go. That'll increase overall prevalence. The older you are, the risk increases. Men are more at risk than women, though both can be impacted. The causes are multifactorial and rather uncertain. Genetics seems to play a role in about 10 to 15% of the cases. There seems to be environmental factors, pesticides or TCE exposure as examples. Wildly, cigarette smoking appears to protect in all population studies. In other words, if you've ever smoked, that seems to ameliorate some of your risk for Parkinson's disease. And there, at least since the MIAC study, what about ionizing radiation? So one of the first things we did is look at a pooled group, the nuclear power plant and industrial radiographer group, and run the standardized mortality ratios. Because if high education reflects low cigarette use, then we would expect a higher risk of Parkinson's disease there and a lower risk of lung cancer. And sure enough, in our group of 250,000, this particular pooled group, that's exactly the way the ratios went. The higher the education, the higher the risk of Parkinson's in that group. And the lower the education, the higher the risk of lung cancer, but the lower the risk of Parkinson's. So that in our group, we look similar to the population studies that appear to suggest that cigarette smoking appears to protect. One of the first studies was of the MIAC worker group by Tamara Azizova, Dr. Azizova and company. And in the MIAC study, remember that these are rather higher exposed populations than in the million-person study, where their highest, are on the order of 2.5 or higher gray dose to the brain. Cumulative brain dose, but you could see that there was a statistically significant positive ERR per gray in this case. And so initially there was some skepticism about that, would we see such a thing in the US populations? So we set about evaluating. In the nuclear power worker and industrial radiographer, since I've been using that as an example for this talk, you can see that there does appear to be a positive trend in some, although not always statistically significant. There seems to be a correlation. Why is not understood, so we continue to evaluate. One of the things that we've done is we did a meta-analysis for each of the 6 or 7 cohorts that have been completed to date to evaluate Parkinson's disease. And I just list here the mean, median, and maximum doses for each of these cohorts overall. And when we pull together the meta-analysis, so this is not a pooled study yet, but it is a commonly performed statistical kind of screening for us to see if this is an important area for us to continue to do work. When we do that, we come up with a meta summary estimate based on 517,000 workers. We see an ERR at 100 milligray that is positive on the order of about 0.2 and is considered statistically significant. We still don't know why. Could it be a co-exposure issue? that people who get dose are also getting exposure to something else that's Parkinson's related, or is it indeed a potential radiation outcome? When you look at, we just don't have a mechanistic understanding, certainly not in the radiation side, but overall, Parkinson's disease mechanistic understandings so far on the biology of the disease include things like the death of critical dopamine neurons. There seems to be an interaction on the nicotinergic neurons, and maybe that's part of the explanation of the smoking, not smoking. There's also dysregulation of iron metabolism. Iron builds up, which causes and increases issues associated with dysfunctional mitochondria. There's significant oxidative stress, ROS, peroxides development that eventually causes death to the dopaminergic neurons. There's buildup of alpha-synuclein that aggregates, part of the important portion of the Lewy body formation. There is associated deterioration of cognitive function. Aging and genetic susceptibility seem to be a part, and then, of course, potential for environmental insult. So more to come on there. It's important that we'll continue to evaluate not just Parkinson's. We're moving into Alzheimer's and dementia, although we don't necessarily expect to see anything there, but we will report back as we do those studies. Generally, the findings to date, based on what I've been able to present so far, except for the heart, most risk coefficients are positive, not in all cohorts, but in many of the cohorts. And they have wide confidence intervals, which is what we would expect for, say, 150 to 110,000 subcohorts. For those single cohort studies to date, the risks are lower in general, for example, like non-CLL, but generally statistically compatible with the studies of the Japanese atomic bomb survivors. Further follow-up in combination with other low LET and high LET cohorts are going to really prove to give us more definitive conclusions overall. Parkinson's disease, that's a new finding. It warrants additional study. We don't understand it yet. And we are looking. So I'm going to turn the talk now toward incidence, chronic conditions, because that could really help us understand what might be going on overall. And so we're attempting to link the million persons, or about 750,000 persons, with the Medicare database, which will allow us claims-based incidence data on many cognitive outcomes, but perhaps as importantly, tobacco use algorithms, chronic conditions, obesity, and diabetes, all potential confounders that we would then be able to have additional information to evaluate our outcomes. Along the way, and in order to do this 50 million person year study, we've had to develop science, and we think that we're now at a stage where the current programs and methods for assessing radiation excess relative risk won't be able to handle all of the million persons, and so we're developing R-based and other approaches, computational approaches, so that we can get all of this huge pooled cohort data together to have a one pooled study, which would be very important. And of course, along the way, we'd really like to integrate epi and biology as suggested and recommended by NCRP 186 and other commentaries. Just to mention a few active NCRP related work. One is methods for and models for estimating and updating the organ doses from intakes of radium. This is so that we can do the definitive radium dial painter study. We call it a complete study because the oldest of the dial painters has now passed, and we have that information. It'll represent 3,200 workers, very important alpha emitter, mostly ingestion, many tissues. We have lifetime exposures, and we'll be hopefully assessing risk with much more updated dosimetry than we were able to do in the late 80s during the last time that this cohort was evaluated. It's interesting that our kinetics now, for example, for skeletal kinetics, are much more improved and could be very important, especially age-based, because many of the young painters began really young, even some of them as young as 11, 12, 13, 14 years old. So it's important to evaluate that. One other mention, we're actively doing a Navy submarine cohort that includes multiple stressors. So not only are they exposed to radiation, but they have bad environment for air. They're underwater for 6 months. The psychology of that, it looks a little bit like being in a can up in space for an amount of time. The only difference is you also have no gravity in space. So NASA's interested in this as a terrestrial group. There's 600, 700 astronauts, but here we have about 150,000 submariners that we'll be able to assess. So you'll hear more about that hopefully in the next year or so. We really think it would be important as a community for all of us to develop much, much more accurate heart dosimetry. Right now, we kind of draw a bag around the heart. And we call that mean dose to the heart. So one suggestion is for NCRP to develop a specific commentary on segmented doses to the heart and other cardiovascular related, maybe kidney is really important, or carotid dose may be important. So we're exploring that. Overall vision casting is we're going to expand the follow-up for nuclear power. And then we're eventually going to harmonize the data and pool, perhaps in 3 or 5 to 7 years. It really all depends on what funding levels we can secure to what I would call a million-person study number 1, where that'd be a milestone in radiation research and radiation protection. But it wouldn't end there, just like RERF did every 5 or 10 years follow-up studies. We should be planning right now and setting up the infrastructure to do that regularly at 5 to 10 year intervals. You can kind of think of million-person study number 2, number 3, etc. In order to do that, we need to train younger folks who can stand on the shoulders of us and continue to do the work moving forward. So we think that's an absolute key moving forward. 1 million persons are keeping me awake. So that comes from The Greatest Showman. You should definitely go watch that. We have really, we're limited only by our resources with this incredible collected set of data. And I appreciate all of the work by literally hundreds of individuals. I'm especially acknowledging those listed here for all of the incredible amount of work over the last almost 25 to 30 years. And I thank you for the opportunity for presenting on million-person study overall.
Dr. Dauer, thank you very, very much for that excellent presentation. Personally, I'm extremely interested, as you know, in central nervous system damage, and your data is, I have some questions later, but I will wait for questions for the people. So for attendees, please, this is open for questions, so I appreciate it. You can make your questions, and I will pass the questions to Dr. Dauer. So I have a first question. Sorry. So in this cohort, did you include the cohort of astronauts or military pilots or commercial pilots that are exposed?
Yep. Great.
It was included?
They have not been included as of yet. Although one of the slide items that I didn't really emphasize much was that we would like to set up, coming out of this work of million-person study, you might call it a national center for radiation epidemiology, which would be natural because we'll have an infrastructure to do such studies moving forward. And of course, pilots would be an exceptional group. All of the groups that we've done so far have actual dosimetry data. That in that case, we'd be one step away. We could definitely do estimates based on flight hours, etc., and understanding of the patterns. And it should definitely be a group. So they're on the radar, but we currently are trying to focus on this million. But very important potential group. Absolutely agreed.
And the other potential group could be people working in particle accelerators around the country and the world. they are, potentially exposed to high LET and more kind of sophisticated type of radiation. That will be interesting to know.
Absolutely. And, some of the cohorts, for example, Hanford and others have rather complex exposure histories. Some folks were in the producing plutonium. Some were in neutron fields, very interesting neutron fields, etc. So we do have some of those exceedingly interesting exposures. But I agree that would be a group that could be interesting.
I have some questions here for you from an anonymous source. Please clarify one of your comments. What cancers are not radiogenic? Can you go for a mechanistic or other explanation? And the second part of the question, any thoughts on cognitive function impacts from low LET radiation? And say thank you for the presentation. So I'm very happy.
Okay, great. So excellent question. So if you look at some of the latest UNSCEAR reports, they evaluate different cancers and potential associations with radiation. And so there are a few where it's questionable whether or not that you would consider an association. Maybe it would be better for me to have said association with radiation rather than radiogenic explicitly. For example, prostate cancer doesn't appear to be directly related, although I would really encourage to go evaluate the UNSCEAR document in that regard. On cognitive function impacts from low LET radiation, the NCRP suggestion was to evaluate high LET folks, but in fact, what I've given you are the low LET radiation results, right? The nuclear power, most of that exposure was from external photon, and industrial radiographers also external photon. So we believe that we need to look for both. And remember, we have the components of dose, even for those that were in a more complex exposure scenario during their working career. So we're hoping we'll be able to tease out if there's any differences between the both. But we agree that low LET will be an important, certainly for cognitive, and let alone all of the outcomes.
Okay, thank you. We have another question from Dr. Sarah Kuti-Walsh. She asks, what population cohort do you use as your baseline, 0 dose, for comparison? Do you ignore or exclude the non-occupational exposure such as personal radiation treatments?
Yep. So the way that for each subcohort and eventually for the pooled group, it would be inappropriate for us to just compare against the U.S. population, for example. Like I said, because of the healthy, and it's important to do that assessment because we see things like asbestos jump up or asbestosis or mesothelioma or any other important outcomes. That might be unique. For example, berylliosis outcome may be unique in a certain particular cohort. So what most epidemiologic studies will do is that an internal within the cohort or within the pooled study. And we know that we have folks that are within the study that have recorded basically 0 or a very low dose over their career, and then we have folks with much higher doses. And so that's what we're using. The referent group are those lower, almost near 0, if not 0, a group when we do those assessments.
Thank you. We have another question from a friend, Sylvan Costes. For more recent studies where biospecimen like blood may still be available, have you explored new IRB allowing obtaining genetic information to increase the power of your epidemiology?
That would be right. Wouldn't that be fantastic if there was some way we could get IRB to agree, for example, to mail a cheek swab to everybody? That would be terrific. It would also be exceedingly expensive. Not to say that we haven't, like I said, a million dreams are keeping me awake at night, and John Boyce, and others. However, we do have particular specimens available as part of the USTUR group incredible for the radium dial painter workers, for example. Many of them donated their bloods and body to science. And so we have that available. We have certain in one case, the NCI NIH went back to some of the higher dose atomic veterans and actually got an IRB and asked for blood and did chromosomal aberration and other translocation studies. And what we discovered for the 16 or 11, I can't remember the exact number that we published on, it correlated to recorded and estimated dose. So that's a real, it's a very, very small study. Wherever we have the possibility, we're doing that. We have not yet explored directly bringing folks back or contacting them, but that is certainly something a future National Center for Radiation Epidemiology could do. And I would encourage, I understand there may be data up in Canada, for example, on workers where you have blood samples from early workers. I would encourage doing those comparison studies because they can help support uncertainty assumptions and conclusions for even other studies.
Thank you. We have another question from Dr. Cody Walsh, and I think you answered partially. The question is, for the astronaut cohort, do you evaluate their personal dosimeter data, onboard detectors, or biodosimetry post-mission?
So just to be clear, the astronauts themselves are not part of the million-person study. NASA is studying the astronauts, a lifetime study for all astronauts. But the short answer is yes, all of that is being performed as part of the NASA studies themselves. I mean, there's a commitment to astronaut health overall. And in addition to that, of course, would be anything we could glean. But it's important to recognize that even for the astronauts, they're a very, very small cohort, 600-ish or so. So it's important for us as we dream big and want to go farther or stay up there longer, that we try to find useful terrestrial analogs as best we can. And then, of course, we'll learn as we move forward. Yep.
Yeah, I want to notice that Health Canada, CNL also was involved too, and the follow-up of the Canadian astronauts on some of the surveillance and some of the blood analysis in the past. And there are plans for the future to continue supporting NASA as a part of the NASA follow-up, the Canadian cohort. So thank you. Another question by Mark Little. You implied that you had to select workers for some cohorts because of expense. How did you sample?
Excellent question. So, for example, in the medical worker cohort, we had information, I can't remember, on many million workers. And so the workers in the lowest dose category, basically 0 dose, there was random sampling in that group. And that's described in any of the cohort studies where that needed to be done. Though that's described in those papers. So it included a defined dose distribution, but then all those in the 0 pile, which made up many millions, were randomly selected.
Thank you. Several kudos for your presentation, Larry. Another question, maybe I missed, but have you included pregnant women in your cohort or separate in the study?
So in many of you mean if you were pregnant when you were exposed, we might have that information in some cases. For example, the radium dial painter cohort, we have almost complete medical information on many of, not all, but many of the cohort members. But we do recognize that with 160,000 women, many of them would have been pregnant at some point in their life time as well. haven't done, we haven't gotten to be able to try to peel out explicit pregnant or not pregnant yet. Certainly something we would like to be able to do if we can get to that information. Of course, it's always about having the information available.
We have more questions. Next one again for Mark Little. You implied that the analysis could be difficult or possibly impossible with the current analysis tools. Was this the reason for using meta-analysis tool as described?
I guess the best answer would be yes and no. Partially yes, in that the currently publicly available tools wouldn't be able to process, say, in our case, more than say 300,000-ish, maybe a little more workers. Given the 50-year-ish person years per worker. So we are developing and are currently at the validation testing phase, computational tools that will allow us to do it. Basically, it's an R-based system that's currently called Colossus. And there'll be a paper about it. There's already one submitted, but there's also a paper that'll be presented at IRPA talking about the development of that program. So that's part of the yes. We don't have tools yet that we could use. But another more important part in the no would be we haven't yet completely harmonized each of the cohorts. That's going to take work and effort because we span over many decades in some cases, and we think that's an obvious, really important tool that we'll describe to transparently say how we're doing that. For example, number of days you needed to work to be in the study. That may have differed over the years in the way that the studies were identified, and we need to harmonize that. So one thing that we're trying to develop in order to give us the tool to be able to harmonize that across these is something we're calling the grandmother database, because grandmothers never forget anything. And in other words, put every one of the million-person folks into one gigantic database where we have their person-level file, a history file, and then, of course, organ doses for each component of organ dose moving forward. And then we can consistently put together a pooled study. So we're working on it as fast as we can, and we hope to get there soonish based on the current funding levels.
I have another question that is related to this. This question is, are you using artificial intelligence in any portion of the million-person study?
So one area where we think that could be very useful, we have all of the, as I mentioned, I'll just give one cohort example. The radium dial painter medical records. We literally have gigabytes and maybe more than that of records available, where AI and being able to read those records and make some sense of them could be made much faster using an AI tool. That's one example. Of course, there are other examples on the dosimetry end where AI or machine learning could help us get to an organ dose much faster, although we haven't implemented those to date. They could be useful in particular organ cases, perhaps. Just to go back to the other question just for a minute, Marcelo, the meta-analysis versus a pooled study. One interesting aspect that I've been thinking about on the million-person study is that in the end, we're going to have all the data. We're going to have the sub-cohort results, and then we're going to have the pooled results. And that will, we can do this kind of with simulated data now to evaluate whether or not meta is, in the case of radiation epidemiology study is a good tool. But hey, we'll be able to assess directly. Hey, here's what the result would be if we did meta-analysis on our subcohort, lower statistical power results versus, a pooled study. So that could be useful for us as a community as well.
Interestingly, there is another follow-up by Dr. Kudi Walsh regarding the radiant dial study. The question is, did you follow up with the children who will have received fetal dose from the radiant dial study?
So we have some information on the radium dial study on those women that had children, but currently we are not following up with that next cohort. We're blessed to even have the radium dial cohort that was put together. Just incredibly, the work was done previously through the 80s, and so we're concentrating on the one that we know we can do and do well now.
Excellent. Okay, I think we have around 5 minutes more before we end the webinar. I wonder, Edward, any question for Dr. Dauer from your side?
Thank you very much, Larry, for an outstanding webinar. And I think my question was about a tissue repository, whether there are ongoing efforts, maybe to add to existing tissue repositories as samples become available to follow up, as you always mentioned, with genetic studies and.
Yeah, absolutely. I mean, we are incredibly grateful to have the opportunity for the USTUR samples that exist, though, and mainly plutonium, uranium. A lot of the DOE workers. We have biosamples there, and then of course for the radium dial painters, we even have blood spots on, say, about 200 of the radium dial workers, which is incredible. Not to mention all of the medical histories, that include, blood counts and other potentially useful information. So yeah, it would be incredible to step into that potential field. Absolutely.
Thank you.
And I think, Edward, you posed a question regarding the molecular and biochemical studies, right? Exactly. Yeah. That will be really important. And Sylvain Costes from NASA also mentioned, it's already published a comment that the Gene Lab and NASA and Ames Research Center have an incredible amount of data that can be will be interesting to add up even more. And also, he suggested, I fully support that, to look at Parkinson's signals or markers to the 3 data. So I think that will be very, very important. So, and thank you, Sylvain, for your comments.
Yeah, excellent. Marcelo and Edward, and actually everyone. I mean, we should be skeptical of the results, right? We're not sure, but because it's an observational study, but we should still be, hypothesizing potentially from a radiobiological mechanistic standpoint. To me, it's interesting that either the iron dysregulation or the metabolic, certainly the metabolic dysregulation, even mitochondrial mess up, and then it's interesting. We're just talking Parkinson's alone, not radiation in Parkinson's, and yet we're talking about reactive oxygen species, oxidative stress, peroxide issues, and the like. So maybe there is a mechanism. I don't know. I think we should do some careful assessing, certainly.
Which is essentially NCRP report 186.
Absolutely.
The need to integrate radiobiology with epidemiology, eventually to develop biologically based dose
understanding.
Models.
That's correct.
Yeah.
There's also a lot of assumptions and in terms of a tissue response, and in particular, central nervous system. So for decades, we said central nervous system is absolutely radio resistant to radiation, any kind of radiation. And we know that is not the case. So even low doses of radiation can produce inflammatory responses and molecular changes that can guide us to understand this kind of correlation with that. So there's a great field to dig into. So I agree.
I think from the cancer standpoint, we have the hallmarks of cancer to help guide us, right? I mean, we can look at those hallmarks, say 6 or 10, depending on which version you're looking at. Do we have similar hallmarks for CNS disease or hallmarks for cardiovascular or cerebrovascular? And if we were to map those hallmarks, whatever those look like, just regular disease, or where does radiation maybe play a role? And I bet you we will find many overlaps, like inflammatory response or cell-to-cell communication or other pieces. So
Correct.
yeah,
So
a lot of
NASA,
rich area to work in, no doubt.
and just a final comment, I think NASA did a good job in terms to define the risk and some of the potential risks. And actually, they mentioned one of those reports that NASA yearly or every 2 years produce, and I think it's a nice guideline to investigate that. Well, I think we reach the end. I will thank you, Larry, for a wonderful presentation, and thank you, Edward, for the interaction with this. I will thank you, the CNL public relation team, to support this effort. Of course, I would like to thank all the attendees to this meeting. It's been great, and thank you very, very much, and looking forward for interactions. So hopefully we can continue this discussion.
And thank you so much for making bow ties cool, continuing the trend.
we will try. We will try.
Thank you very much.
Best instructor, Larry.
All right, be well. Thank you very much.
Thank you very, very
Okay,
much.
thank
to
you for the
everybody.
opportunity.
Thank you.
Okay.
Thank you. Bye.